Welcome to videos on analog electronics laboratory experiments. In this video, we will see DC power supply design. Before we start, let us go through the initial slides of this video. Okay, with these initial thoughts, let us start the design of DC power supply. So, the input for this particular experiment is the AC voltage. The output we are expecting a DC voltage. Uh, when I say AC voltage, we are talking about a AC signal of 230 volt RMS with 50 Hertz signal that is given to a step down transformer. This is a step down transformer so that we can operate with reduced voltage. Then comes the rectifier. So this can be either half wave rectifier, full wave rectifier using two diodes, or it can be another full wave rectifier using the bridge configuration. So these are the three possibilities of realizing this rectifier, which will give a pulsating. So this is giving a pulsating DC, which will be filtered using a filter. Typically a C filter is used to filter out the AC component. Then we'll have a DC voltage with reduced AC component. Then we're going to have the final stage, which is a regulator. So let me write the regulator here. This is a regulator. This is typically an integrated circuit. So here we'll get a pure DC signal. So here this is the stage. So this is a AC signal. This will also result in a AC signal. Here it is there is a DC signal with some AC component. Here this is a DC signal plus some ripple will also be there. Here it is a pure DC signal. So that's what is different stages of realizing a DC signal from AC. This is how it proceeds. Now let us start with replacing each of the block using the circuits now. So we know that a step down transformer will have a primary with more number of turns and a secondary with lesser number of turns, which will result in a step down voltage. This is 230 volt, 50 hertz AC signal. This will result in a reduced voltage. So this can be a 909 volt transformer. So this is 9 volt. This is again 0 center tapped transformer. This is again a 9 volt transformer. One of the possible rating of the transformer. This rectifier. So let us start with a very simple rectification of half wave rectifier. You can think of a half wave rectifier. So this is the half wave rectifier. This is a resistor R, which is a part of your rectifier. Then comes the filter. This is a value of C we will going to design for required amount of ripple voltage. And then we have the regulator IC. That's what is this regulator IC. So this is going to have an input terminal, output terminal, and there's a ground terminal. It's a 3-terminal IC. So this can be suppose if you're looking for a positive voltage, it is one of the example is 7805, which will going to give you a 5 volt DC signal. So this is the typical ground of this. and this is the output. Here you can connect a variable load which will going to draw certain current from this regulator, so that you can get the DC voltage of desired current. So this is the flow now from AC step down transformer from 230 volt to any desired voltage. So whatever 230 volt, 9 volt is written, these are all the root mean square values, RMS values. And we have a rectifier which is half a rectifier with a resistor. Now this will represent the rectifier. Then comes the filter to get a ripple to remove a major part of the AC component, and then comes the regulator which will give only the DC signal. AC signal is totally suppressed over here. So this is what is the overall circuit diagram of a DC power supply of getting 5 volts with uh, using a half wave rectifier. So let us now do the design part of it. So now while doing the design, so this is the design part of it. So before we start the design, so we know that output required is a DC voltage, and the input that is required is a AC signal, voltage signal. So we do while designing, let us do a top down approach. This is top top to top to bottom. So this is top to bottom, this is the top mode portion, and this is the bottom. So now when I say top to bottom, so now we start with, so what is the voltage required, and then we go stage by stage backwards, and then finally decide what is the rating of the transformer. Fine. So now if you are looking for a 5 volt DC output, a 5 volt DC output, we have to have the last stage will be a 7805 regulator. This is a 7805 regulator. So this is a 7805 regulator. So what is the requirement of this regulator? Let us see the data sheet of this regulator, and if you can see there, you will come across some specifications of that. So if I open that data sheet, you can see now this is what I have for 7805. Let me just expand it. This is 78XX. This XX can be, you can see here the output voltage can be 5, 6, 8, 10, 9, 10, 12, 15. These are the possible voltages, and output current up to 1 ampere we can able to draw. So this is what is the 3 terminals of the regulator. So first one is input, second terminal is ground, third terminal is output. So let us move down and try to find out some specifications of 7805. So this is the block diagram of that IC. So this is, we are looking at this electrical characteristics of LM7805. If you can see now, the output voltage is typically 5 volts with a minimum of course it may just give 4.75 also as the output voltage, it can give 5.25 also. So this is the possible output of this particular IC. So provided the condition is that the output current that you are drawing should be up to 1 ampere, and the input voltage should be minimum 7 volts to maximum of 20 volts. So this is what is important now. So now to get an output voltage of 5 volts from a regulator, I should give minimum of 7 volt and maximum of 20 volt. So let us go down here and then try to find out what is, how does this is useful in designing our circuit. Now I know that this should be the regulator. The regulator, if it has to give 5 volt, this is 7805. If it has to give 5 volt, this is pin number 1, 2, and this is 3. 2 is grounded, 1 is the input. So what is the minimum voltage you require? So minimum voltage is 7 volt, the maximum should be 20 volt. So this is what is the range of the voltage that you can apply. So let us take a voltage of more than 7 but less than 20. So let us take it around maybe 12 volt. So 12 volt is the voltage that is required at the input so that you can get 5 volts per curve, because 12 is more than 7 but it is less than 20. This is fine. Even you can take 10, even you can take it 8 volts, or even you can take 15 volts, that is fine. Let me select it as 12 volts. Now, so this is what I will. We're just going from top to bottom. So now once you get 12 volts, now this is a stage where you have something like this. So now this is the input for this is a filtered waveform. We know that suppose you write the waveforms at each and every stage of this particular circuit. Let me just write that. So now if I want to write uh, this is my input signal. The input signal will be a sine wave at this point. Okay, let me say it as at 1. So now when I don't connect the capacitor, so what I'll be getting is without this capacitor, if I have only this much, so I will get. So let me write it here only. So if this is of some V peak voltage, the output voltage at this point with rectifier will be slightly less than the input voltage by V gamma. You can see this is what we want to get. So you can see this is at 2. This is at 2 without the capacitor. The moment I put the capacitor, suppose if this is your first cycle, so it just goes like this, and then from here it goes down, and then it goes up, and then it goes down. So this is what is the waveform at 2 in presence of capacitor. So once I put the capacitor, so now this is the input voltage that will be applying to 7805. So now what is the waveform that you are having at the input of regulator? At the input of the regulator, from this entire series, from this entire set of the circuit, you will be having a waveform at this point as something like this. So it just goes up, comes down, goes up and comes down. So this is what is the ripple voltage that you are having at the input of 7805. This is what we want to have to be 12. So meaning the bottommost voltage, let it be 12. Let it have, because this is a ripple, this is having some ripple. So let us assume a ripple of 1 volt. If this is 12, if the ripple volt is 1 volt, then actually this is 13 volt, correct? So now what are the waveform you are looking at? So this I want it to be 12. I want to have a ripple of 1 volt. So naturally this will be of 1 volt. So this will be of 13 volts. This will be of 13 because 12 plus 1 is 13. So what you want at this point? I want to have a waveform of 13 volts at the peak. So this should have a waveform. Now I'll put the capacitor. This voltage, the capacitor voltage, should have a voltage up to 13 peak. It can go up to 12 down. It should again go to 13. This is how it is going. So now this is done. Now let us go one step behind. So let us come back and try to design the value of C later. So what do you have? You have a resistor and you have this. See now, this is at this point you have a 13 volt and 12 volt. So what you are expecting here, because this is a diode, this will have a drop of almost 0.7 volts. That by the time it comes over here, can you see this voltage? The voltage over here should be, suppose if you want to have a waveform of 13 volts here, then this should be 13.7 volt as the peak voltage. If the peak voltage is 13.7, then I can get 13 here. So now what do you have? You have a transformer. You should have a transformer whose voltage is 13.7 is there. Let it be 14 volt peak. 14 volt peak should be there here. If you're considering this as 0 and this as 14 volt peak, of course this is your 230 volt supply. This is 230 volt AC. So now you can see how we are going down from top to bottom. So now what is the rating of the transformer? The rating of the transformer is 14 volt peak. Usually the rating of the transformer is put in terms of RMS. When it is RMS, so what is the relation between V peak and RMS? RMS. So RMS is always V peak by root 2. So I have 14 volts by root 2 will be my RMS. So how much is V peak by, that is 14 divided by root 2, it is 9.89 volt. 9.89 volt. So 9.89 volt will be the RMS that is required here. This is 14 volt peak. Can I write it as simply 9 volt and 0 here? 9 volt and 0. So what is the design now? So the design what I have is, this is my 230 volt, 230 volt. This is 230 volt AC 50 hertz signal. So what is this? This is I want to have this is what, 9.89. So you will not be having 9.89 volt. Assume that you have a 9 volt transformer. So let us select a transformer with 9 volt and this is 0. This is 0. Or so let me select a 909 transformer. So what I'll do, I will select this. So now you can see this is a 230 volt input AC. I will select a 909 transformer. I will not use 9 and 9 extreme, but I'll use this 9 and I will use this 0 as my reference. This is my reference point. I will not be using this. Suppose if I use this, then this will become 18 volt. 18 volt is not required. So how much I want is 9.89. Let us select, if I use 9, will it work or not? So I'm using 9. What is 9 into root 2? This is 9 volt. This is 9 volt. 9 volt. Just give me a minute. This is 9 volt. So once you have a 9 volt RMS, its peak is 9 into root 2, which is 12.72 volt. 12.72 volt is the peak voltage. Then you're going to put a diode, and this will be of voltage how much? There will be a diode drop of 0.7. Can you see now it's almost 12 volt. Then we're going to put a resistor of 1 kilo ohm, let us assume, and then let us put a capacitor. Let us find out this capacitor value later. This is grounded. You can see now you will end up with a ripple voltage something like this. So now this is 12, this is now 11. See now you have a voltage which is having a ripple of 1 volt, and the minimum is from 12 minus 1, it is 11 volts. Is this 11 volt insufficient to give a constant phi? Yes, it is sufficient, because you need to have minimum of 7 volt. Since this 11 is greater than 7 volt, then I can use 7805 volt as a regulator, and I can easily get the 5 volt constant voltage. So now the question is, what is the value of C? What is the value of C? So we need to find the value of C for to get a ripple of 1 volt. So let us find the value of C to have a ripple voltage of 1 volt from this input signal. So now what is V ripple? So there is an expression for V ripple voltage. V ripple is given by the peak voltage, that is V peak at this point. V peak at this point divided by FRC. FRC. So now you have peak voltage, which is the peak at this point, which is in this case 12. So here it is 12 divided by how much is frequency? Frequency of the signal is 50 Hertz. The R value, you can take it as 1 kilo ohm. It's not only 1 kilo ohm, so there is an input resistance of this also, which will also be 1 kilo ohm. Now while designing this circuit, even you can take out this 1 kilo ohm resistor. You can take out this 1 kilo ohm, whatever resistance that is there as the input resistance, that itself is taken as a resistance. Maybe you can take out this resistor. This will act like the resistor. So this is 1 kilo ohm. Now you can find the value of C for a ripple voltage of 1 volt. So now what you have, 1 volt is equal to, the voltage here is 12, that is V peak, divided by F R C. So C I can find. So this is 12 by 50 into 1K into C. So I have to find the value of C now. So it is now 1 alpha equals, upon the parenthesis 12, this is 12 divided by 50 into 1 exponential 3 into alpha A, close, shift cal will give me a value of C is equal to, C is now 240 microfarad. 240 microfarad. So now what is the design I have? So let me rewrite the circuit now. So I'm using a 230 volt 50 hertz AC signal given to a transformer of, this is 909. I'm using just 9 and 0. I will use a rectifier. I'll use a diode. This is my capacitor of, okay, since the calculated value is 240 microfarad, assume that in the lab I have 470 microfarad. I'm using the available capacitor of 470 microfarad. This is 7805, and then I'm grounding this, and so now this is 9. So this is 9 into root 2. How much is that? 9 into root 2 will be 12.7. Here it is 12. So V peak is 12 volt, and at this point, and what is V ripple now? V ripple is equal to 12 by 50 into, okay, this resistance you can take it as 1 kilo ohm into the capacitor used is 470 microfarad. I can find out how much is V ripple. So it is 12 divided by 50 into 1 exponential 3 into 470 exponential minus 6. So you're going to get a V ripple of 0.510 volt, that is 510 millivolt is the ripple. So if it is 510 millivolt is ripple, the waveform over here will going to have 12 volt peak, and it is a ripple of hardly 500 millivolt. So minimum what you want to get is 11.5 volt. 11.5 volt is sufficient to give a constant of 5 volt, a constant of 5 volt here. So this is your DC voltage, correct? So now with this design, you should be comfortably getting a 5 volt DC signal. So let us do that now. So let me, you can see I'm having a diode here. This is my diode. This is a 470 microfarad capacitor, electrolytic capacitor. So this is my connection board, and this is my transformer. This is a transformer. This is a 909 transformer. Let me use this. On the rating, you can see it is written as 909. Can you see it? This is 909 transformer. So let me use as per my design. So I can use only the center tap, and so I'm just doing the connection now. This is what is 909. So let me connect it to that will go to anode part of it. This is grounded. So I have the diode here. This is diode. The anode will go to this. Anode will go down here. This is cathode. I'm just digging up this circuit so that I can show you the output. So this is the circuit I'm digging up. You can see this is a 230 volt signal, so that is going from my mains. This is a transformer 909. I'm using only 9 and 0. Coming to the diode, this is my cathode. To the cathode I'm connecting. Okay, here you have to be careful. So this should be plus, this is plus, and this is minus. And I'm connecting the same. This is minus here, so I'll connect the plus to this, and this is minus connected here, which is to the ground. Okay, that's what I'm connecting here. So no need to connect that resistor now, because the regulator input itself will act like this is 7805. So let me connect these two. So this is the input. This is first terminal is input, second terminal is ground, third terminal is output. I'm connecting this to the input. This is grounded. This is grounded here, and then we'll see the output. So this is the output. Output is left open so that you're not drawing any current from that. So output voltage should be typically 5 volts. So this is, we have done a top to bottom approach for designing this. So from top means it's from final output voltage back to what is the design. Next, while testing, let us go from bottom up. Bottom up means from this supply voltage, we'll see the step down waveform, then the filtered waveform, then the final output voltage. So it is now bottom up for verification. So now the analysis that the verification is now bottom up. So from bottom to up you go. So it's now bottom up. So let me see the voltage now. So I have a voltmeter. So now I'll measure the, you can see now I'm measuring the AC voltage. If you can see, this is a multimeter, this is AC RMS voltage. If you measure this RMS voltage of the output of this secondary of the transformer with the center tap, this is a 909 transformer. Let us see how much is the voltage that I'm getting. See, 90, I was supposed to get 9 volt, you're getting 10.44, it is fine. So I'm getting a voltage of 10.44. This should give me a RMS of how much is, this is RMS, the peak voltage will be 10.44 into root 2 will be 14.7 volts. So now V in RMS is 10.44. So then the peak voltage would be 14.76 volts. The peak will be 14.76. So now let me observe the waveforms using the analog discovery on the scope. So I'm just using analog discovery to measure the voltages. So I'm connecting these to ground now. So I'm just connecting the ground, and the input I'll connect it at the input of the diode, the anode of the diode. Let me see what is the waveform. This is, so I'm trying to see the waveform at, so let me just, because it is 50 Hertz, let me make it around 5 millisecond per division. Since I'm looking for a larger voltage, let us make it some 5 volt per division, and this also like, okay, 5 volt per division. And let me run this. You can see now I'm getting a input voltage of sine wave. So let us measure what is the amplitude. So let me measure the input. This is defined measurement, channel 1, vertical, you can see what is maximum voltage. You can also find the frequency of the input signal, which will be 50 Hertz. See now input is 50 Hertz signal, the maximum is 14 point something, that is a peak voltage. So that's what we wrote here. The peak voltage should be 14.76. Okay, let me just put this aside. Okay, so now this is, let me show you simultaneously both of them. So this is what is expected voltage, 14.76. You're getting almost there, 14.3 something. So that's the waveform that I'm seeing here. Let me connect second channel over here so that you can see a filtered waveform. So I'm using second channel to see at this point. You can see this is my, see now this is you can see this is blue is the waveform where you are expecting something like this. You can see this is what is expected. Can you see this is rising a little bit and then it's again coming down here. So you can actually measure what is the ripple voltage of this. So we will measure the maximum and the minimum of this second waveform, that is the channel 2. So what I will add, I'll add the parameters corresponding to, give me a minute. So okay, it's, I just expand this and then I will add parameters of C2, which is a vertical. Let me measure maximum, minimum and the peak to peak. See now maximum is, let me stop this for some, you can see maximum is 13 point something, the minimum is 13.49, the peak to peak is 226 millivolts. So this is what is the ripple voltage. So ripple voltage is now reduced because we are using a 470 microfarad capacitor. So we'll just verify what is the expected ripple from the equation and what we are getting. So let me note down how much is the ripple I'm getting. So now so at this point I have a input voltage something like this. So this is 13.65 and this is 13.42 and V ripple is hardly 226 millivolt. So this is the reading what I have now. This is the reading what I have. See now the reading what I have is the input maximum of your ripple is 13.65, the minimum is 13.42. Of course this is certainly more than 7 volts, so this is sufficient to give a constant 5 volt. The ripple voltage is 226 millivolt. So using the equation, if you want to verify what is the V ripple voltage that you are supposed to get now, so shall I use that equation of V ripple? I'll come back to that. So V ripple is now, so V ripple voltage is, so let me write it here. So it is 13, V peak is 13.65 divided by 50 into 1k into 470 microfarad. If you do that, I'll get the ripple voltage. 13.65 divided by 50 is the frequency, 1 exponential 3 is the resistance of your input resistance of the regulator, 470 microfarad is the value of the capacitor. If you do that, I should get, of course, it's around 580 millivolt is the expected value. You're getting less than that, it's not an issue. So you're supposed to get, now the resistance may be slightly different. Now maybe the resistance is a bit more okay, larger compared to what is our expectation. So you're getting a ripple voltage of around 220 millivolt. So this is 480 with an assumption of this is around 1 kilo ohm. Maybe this assumption is not correct. If you take it as 2 kilo ohm, then this comes out to be almost close to 226 or 220 or 230 millivolts. So that's what is. Of course, you'll get close to 280 millivolts. That's fine. So now we have a ripple voltage of less than what is intended. So that's fine for us. So now what we have at the input of the regulator, a voltage which is always more than 7, and it is less than 20 also, Now what I'll do is I will now connect. You can see I will show you what I'll be doing now. So what I'll do now is, so I will connect, I'll show you what is the input to the regulator and output of the regulator. So this is now, let me put the channel 2 to the output of the regulator, channel 2, and channel 1 I will keep it at the input of the regulator. So input of the regulator. So input of the regulator is a slightly ripple voltage, whereas the output is a constant 5 volt. Okay, let me run now. See now, this is the input of the regulator. This is the output of the regulator. Can you see the output of the regulator? This is C2. I'll just delete all these things and let us measure what is. Okay, let me just delete all of them, or let me just clear all of them. Now let me measure what is the average voltage of the C2 channel. This is, let me measure the average. Since you are using a 7805, you have to get 5 volt. So channel 1, what is maximum, what is minimum, what is peak to peak. See now, let me stop this. Can you see C2 average, that is DC voltage, the output voltage, is it exactly 5 volts? Can you see C1 max and C1 minimum is above 7 volts? Can you see the peak to peak voltage almost 200 millivolt? So this is what is intended. So our intention was to get a constant 5 volt from a pure AC signal. So this was AC signal, then you got a pulsating, then you're getting a constant 5 volt. So this is the entire flow. So from this entire analysis, you can see you are getting a constant 5 volt from a pure AC signal. If I want to show you the input AC signal, I'll go and connect at the input of diode, that is at the anode of the diode. If I run it now, you can see the input is sine wave. Can you see this is input and this is output? So what is the input? Input is a 9 volt RMS and output is a constant 5 volt regulated power supply. Fine. So this is the entire flow. While designing, we come from top to bottom. While analyzing, we'll go from bottom up. That is, we start with the output of the transformer, then the rectifier, filter, and then the regulated output. Fine. So just try to understand all these concepts so we can very comfortably do the experiment. Thank you.